Okay, the third part of this discussion will talk about how the chunks created by the splitterators are processed in parallel via the common fork join pool. And we'll talk briefly, I'll kind of reiterate briefly how the common fork join pool is implemented. You've already seen bits and pieces of this when we talked about fork join pool, so I'm going to go through it fast, and I'm going to look at it from the point of view of how the streams framework behaves, the parallel streams framework behaves, but some of this will be a little bit of review. So the chunks that a splitterator creates are going to be processed in the common fork join pool. And remember, there's one common fork join pool. So I shouldn't say in a common fork join pool. It's in the common fork join pool. And if you recall, the fork join pool provides this high-performance, fine-grained task execution framework for data parallelism in Java. And why that matters is because the parallel streams framework and the completable futures framework, which we'll talk about after we get done with parallel streams, are consumers of the parallel processing engine provided by the fork join pool. And there's actually other stuff above and beyond parallel streams and completable futures that use the fork join pool. Things like the Kotlin coroutines are used. They use the fork join pool. Scala parallel computing, Akka parallel computing, they all use the common fork join pool as well. Or they use a fork join pool. They may not use the common one. Internally, the fork join pool implements the executor service interface. If you take a look here, you can see we have the executor service with abstract executor service and the fork join pool. And then there's a thread pool executor and a scheduled thread pool executor. We're not going to talk about those in this class. We will talk about the fork join pool. And the fork join pool executes fork join tasks, which is essentially this chunk of data along with some computations that perform fine-grained parallelism on that chunk. If you recall from your assignment 2A and 2B, the way you do this is by having the compute method that will work on the chunk, and then the compute method can recursively split things up into smaller fork join tasks and then join them back together again, blah, blah, blah. The great part with the streams framework and parallel streams is all of that forking and joining is hidden from you. Fork join task is just a lightweight, it's lighter weight than a Java thread. A thread has extra stuff. A thread has registers. It has a runtime stack. It has thread local storage. It's got all this extra state because it has to actually be capable of running on and being suspended and resumed and so on by the underlying processor core or cores that are running the threads. In contrast, the fork join task is really lightweight, but you can have lots and lots of them. If you tried to have thousands of Java threads, Java worker threads, your system would just melt down. The operating system would get overwhelmed unless you had just a ridiculously gigantic multi-core processor under the hood with gobs of memory. In contrast, you can have thousands and thousands of fork join tasks, and they're just little objects that take their turns running on the underlying worker threads in the fork join pool. Therefore, you can think of a parallel stream as a user-friendly facade for the fork join pool. So when we program with parallel streams, we think in terms of aggregate operations like map and filter and collect and so on. But under the hood, things are processed using the fork join semantics for the chunks that are spit out by the splitterators. It is possible to program the fork join pool API directly as you have done, or as you were doing, but as you will see, it is painful. And I think you'll see when we do the next assignment, assignment 3, how much your code just sort of evaporates, even though you're going to be using sequential streams in conjunction with a fork join pool. So it's not hideously complicated. It's way, way simpler just to use the parallel streams framework. All the other stuff just disappears. And for those of you who are fans of The Lord of the Rings, you'll probably remember this famous sequence between Saruman and Gandalf. And I have an example that shows how to compare and contrast with an apples-to-apples approach, the fork join pool way of doing things versus the parallel streams way of doing things for the same processing in the search stream gang application. There are, however, some types of algorithms that don't really match the parallel streams programming model very well. There's one that you can take a look at here in this article at the bottom of the page, and it's basically directory hierarchy traversal program. And I think I've written it both with parallel streams and with fork join pool. And I think the fork join pool is arguably a better way to go for this. You could actually, so I think it's probably arguably a better way to go. I'll leave it at that. And you can take a look at the code in this example. And I actually have my own variant of this in my live lessons repository. All parallel streams in a process share the common fork join pool in order to optimize memory utilization. And what that means is that all the threads in the pool, all the threads in the common fork join pool will take any chunks created by any parallel stream in the same process. Now, obviously, if you have different processes or different computers, they're not going to share the same pool. But if they're in a process and you have multiple parallel streams, all the processing, all the aggregate operations, and so on, the terminal operations, intermediate operations that are created will use the same fork join pool. And the reason for this is just to optimize global use of memory. There are very few knobs to control the common fork join pool, or any fork join pool for that matter, but definitely the common fork join pool has a very few number of knobs. And if you want to learn more about why that's the case, you should watch this great video by my friend Doug Lee, who wrote all this stuff. You can find it at YouTube. And he explains sort of why they did the fork join pool the way they did it. And it's really, really, really interesting in terms of thinking about how to optimize the performance of parallel computing applications on modern multi-core processors. And a lot of the stuff there is non-intuitive. In contrast, the thread pool executor framework, which we won't really cover in depth in this course, but we'll cover in the spring, has lots and lots of knobs. You can configure the size of the fork join pool, the common fork join pool, in one of two ways, right? You can either use the system.setProperty method to control the common fork join pool size by giving it the number of threads, which we've talked about before. Or you can use the manage blocker stuff, which is shown up here. So those are the two ways to do it. And we'll talk about that again briefly. All right, just a quick recap of what a fork join pool looks like internally. You guys have seen this, so I will go through it very fast. But now that you've had a little bit more practice with it, it might make more sense. And it'll also make a lot more sense when you think about how the splitterators work in conjunction with a fork join pool. So when we talked about this before, we didn't really cover splitterators. Now that you've learned about splitterators, some of this stuff may make more sense. Every worker thread in the fork join pool runs a loop that scans for subtasks to execute. The goal, as you'll learn if you watch the Doug Lee video, is to keep all the worker threads as busy as possible and the cores as busy as possible. A worker thread will only block if there is absolutely nothing left to do. So the goal, that's why you want to have that's why you want to have a single common pool, so it can throw as much work into that common pool as possible in order to be able to keep the processors running as much as you can. Why does this matter? Because blocking cores is very costly. And again, if you watch the Doug Lee video, he explains this. But modern processor cores do not like to go to sleep. They're sort of insomniacs, and they like to stay awake, and they like to do something. They'll even spin. They'll even spin for some period of time. In some cases, it's preferable to have them spin and do nothing rather than have them go to sleep, because it takes so long to start them up again. Therefore, each of the worker threads in this fork join pool will keep checking multiple sources of inputs to find things to do. And it does this in a very clever way using randomization. Again, as we talked about before, the worker thread has this DEC, or double-ended queue. That's the main source of input into a worker thread. That's implemented internally by this worker queue class, which is nested inside of the fork join pool class. If a task that's running by a worker thread calls fork, or as is the case with the parallel streams framework, if the framework internally calls fork, because remember, you don't call fork with the parallel streams programming model. The framework calls fork on your behalf. In that case, the new task is pushed onto the head of the worker's DEC. The worker thread, when it comes up for air, will process the elements in its DEC in LIFO order, which is last in, first out. And what that means is it pops the subtask off the head of its deck and then runs it to completion. The only way it would ever stop running would be if it blocked on a synchronizer or I/O for some reason. We've mentioned before that join pitches in to pop and execute subtasks. So the goal is to try to keep things as busy as possible. That's the Jiffy Lube model of processing. And the reason for using LIFO is to improve the locality of reference and the cache performance. And the idea being, what LIFO means, fresh work before stale. So if you just put something on the front of the queue and then it's time to figure out what to do next, if you take the thing off the front of the queue that you just put on, chances are it's got all of its stuff warm and ready to run, and you don't have to go back out, or not you, but the system and the underlying infrastructure doesn't have to go back out, pull data in from various caches, refresh caches, and so on and so forth. It's all kind of warm and ready to go. Obviously, the fork join pool uses work stealing, so it tries to keep things as busy as possible. The stealing is done randomly, so you don't always try to steal from the same place. You randomly steal from different decks to try to smooth out contention for locks. Tasks are stolen in FIFO order, and this becomes really important to understand when we think about how parallel streams works. And I'll talk about this as we work through the discussion here. So FIFO, of course, means first in, first out. That's just typical queuing behavior, like if you wait in line to purchase tickets at a movie theater or get popcorn, or you wait in line at the security screening at an airport. That's FIFO order. And the reason for doing this, the reason for stealing the tasks in FIFO order when a given worker thread pushes and pops in LIFO order is to try to minimize contention from the thread that owns the deck. So the thread that owns the deck will take things off the front and put things off the front. Threads that want to steal from that deck steal from the end. And if you've got a bunch of items in your queue, then you can actually avoid any contention because they have two different locks. There's a lock for the front and there's a lock for the back. And as long as there's not a single item in the queue, in the deck, then you don't have to worry about trying to contend for a single common lock. You just have to worry about things at the end or things at the front. Now, this is another important thing. The older stolen task may provide a larger unit of work. And if you think about how splitterators work with parallel streams, they start with the entire thing to do, and they split it in half, and then they go ahead and basically add that to the queue, to their deck. So if you think about what happens, things are stuck onto the deck with the biggest items at the end, and then the next biggest in front of that, and the next biggest in front of that, right? Because every time we split, we make things half as big, right? Or hopefully we make it half as big. So you're basically going to have sort of like an inverted pyramid of sizes in your deck. So therefore, if you steal from the end, you'll be stealing the biggest size items, which is exactly what you want, because then you can start with a big item in your new thread and start chunking that up into pieces. So you're always working on the biggest size units that you can. And so that means that the system will behave more optimally in the context of parallel computing, because it always makes sense to parallelize things that are bigger rather than focus on parallelizing things that are smaller, because you get a bigger bang for your parallelism buck by doing it in that particular sequence. Again, as we talked about before, the work queue deck tries to minimize lock contention, and it does that by having push and pop only ever called in the same thread, which means you don't really have to worry about contention a whole lot. You can use these so-called weight-free compare and swap operations, which are super duper optimized at the hardware level to make as short a period of time that you get a critical section as you possibly can. In fact, there's almost never any contention here. It's only if you have like one item in the queue or the deck that you'll ever have contention. If someone tries to steal, you have to be prepared for that. Yeah, question. How do you make sure the size of the task? Well, that's because of the way that splitterators work. Remember, with a splitterator, you start with the entire thing that you're going to work on, like the entire array, and then you split it into two chunks. So you start by putting the biggest thing into the deck. Then you take that biggest thing out, you split it into 2 chunks. You push the bigger chunk on. Then you take the next thing, you split that in half. You put the half in there. So it basically looks like a big inverted pyramid of sizes. Right. Things. I think your question is things run in parallel. Splitting and stealing run in parallel. Pop can be called from a worker thread to steal a subtask, and that may actually have to block or wait. It doesn't just loop in a busy way. If you want to learn really low-level gory details about this, take a look at the implementation of the fork join pool, and there's actually a comment section called the implementation overview that explains it and gives pointers to other places to go. Okay, that is the end. Please keep working on your programming assignments and let me know if you have any questions.